Okay, we are recording now. Going over Michael, Chad, Annie, Ann, Sally, Jaron, No Toussaint, Tori. Okay, you all have your homework to turn in?
It's uploaded, is that fine?
It's uploaded? Yeah, that's fine.
Oh.
Yours uploaded.
We could turn in a hard copy?
Well, you could have done that too, yeah.
Then why was the due date or the due time today?
Because it's due before class starts.
But that's
An hour
before.
Oh, it was supposed to be 11:30. My mistake. It was supposed to be before class starts. My mistake.
One problem's worth of extra credit.
Or now you can extend it for another hour after class.
I think you can understand because our class on Monday, Wednesday, Friday is 10:30. I was just thinking.
What, you don't think the extra 1 hour out of a month will help that much?
A little more than a month, but I think I've mentioned this to a few people. It is quite distressing to me that people basically hadn't started until this past weekend when I've been extolling you on you should be doing problem one and problem one the first week of school, problem two the second week, and yeah, that was troubling to me. I'm not sure why that disappeared. Okay, today we're going to talk about Ampères Law and the Biot-Savart Law. And Toussaint isn't here to correct my pronunciation of these French words. These are people's names. Ampère, which we'll just say Ampère because I don't speak French. Does anybody else here speak French?
Oui.
You do?
No.
That would be non. Non. N-O-N.
No.
But then again, he was being honest and saying no in Spanish. I am a funny man some days. Today's not one of them. Okay, so Ampères Law, In 1826, André Marie, that's a gentleman's name, developed his famous law. And this law is a lot like Gauss's law. You can see a variation here. I put this middle part in to make sure we understand one simple thing. Why current is technically not a vector. This here is the technical definition of current. J is the current density vector, and then you integrate that vector over an area with a dot product, and you get a scalar. And so it's because it's an integral of a vector dotted to a vector that it's a scalar output. So, go ahead.
Where is this coming from? I'm missing what.
Well, what I'm talking about right now is just the stuff that I put the green around, the definition of current. Right, the definition of current is that current is equal to the integral of the current density, which is the current per unit area, dotted to the area. And that's why current technically is not a vector.
Is it a double integral or?
Well, it's an integral over area. So yes, it's going to be. Well, it'd be double unless you do some trick like, on the test, or at least with what we were looking at yesterday. A triple integral, you just make it a single integral by saying, okay, well, the area is constant of this equation for some given radius, right?
Oh,
so you took a triple integral and made it a single integral. But it has to be an integral over the area. And so if you don't make any simplifications, it's a double integral, which is why I put it that way here. Okay, so what does Ampere's law say? Well, it says that the magnetic field created by moving charge depends on the current that is traveling through some closed loop. And so the simplest situation to apply Ampere's law is here with a current carrying wire and find the magnetic field created by that wire. So in this picture, I have shown a radius r. I've made a circle for my path. Why did I make a circle for the path? Okay, it needs to be closed loop, but a square would have closed it as well.
Symmetrical this way, and then no memory.
Yep, because of the symmetry. We know that magnetic fields always form closed loops. And the only closed loop shape that works with a wire of infinite length is circle going around the wire. And so, without knowing anything about the magnetic field created by a current going through a wire, other than apparently by experiment we can see that it creates a magnetic field, we know that it has to be doing circles. Right? It's an argument just based on logical thinking, not based on any physics laws, so to speak. So we make a circular path based on the symmetry so that everywhere in this path, the magnetic field dotted to, I don't remember if I use DL or DS, I'll use DL here. They're going to be either the same direction or anti-parallel. That is, it'll either be plus BDL or minus BDL. And so I'll just make kind of an arbitrary decision and say that's plus BDL. It's not truly arbitrary. I'm going to find the magnitude here, and then from experimental measurements, we determine the direction, and that's what gives us the right-hand rule. So here I'm just looking at the magnitude, so that's why it's not really so much arbitrary as saying, okay, the magnitude is going to be BDL regardless.
Wait, DL being changes in the wire.
DL, okay, L is the length, so DL is a little piece of length along the wire. That's right.
Oh, of the loop?
On the loop, yeah. Now keep in mind, there's not really anything doing this loop. That is a calculational loop only. But we devise that loop, so B.dl is equal to BDL on the loop. Why? Because of the circle matching the symmetry. So then, the left side of Ampere's law and then we once again just look at symmetry. No physics reason for this, just symmetry. The dictates of symmetry are that you cannot have the magnetic field strength change if you're a constant distance from the wire, because the wire simply doesn't care what angle you look at it. The symmetry says it's going to look the same from any angle. So the dictates of our symmetry also say that the magnetic field is going to be constant if I stay on a constant radius loop centered on my wire. So that's going to be integral of B, or B integral of DL.
Wait, what are you saying right now?
The magnetic field has to be constant if I am staying a constant radius away from the wire. And once again, that is just a symmetry argument. That's not based on any significant physics ideas at all, just based on symmetry. Well, now that we're down to this, integral DL along a circle is what we call the circumference of a circle. Now, we went through this in class yesterday. Yesterday? Yeah, yesterday was Monday. But in class yesterday, we didn't do the calculus ideas. It was more just, okay, so it makes a circle and not so clear. But this is obviously going to be B times 2 pi r. So that's the left side of the equation. Now, remind us what Ampere's law is. That is a poor circle. Integral of B dot dl, the so-called circulation, is equal to mu naught times the current that's enclosed by my circle. So the circle is not a real circle. It doesn't really exist. I'm using it for calculation, and then I'm saying now what current passes inside of that circle I use for calculation. And in my picture, it's really clear. It's a single wire carrying current I. And so that's just going to be U naught I. And so I end up with my relationship B times 2 pi r is equal to mu naught I, or B is equal to mu naught I over 2 pi r. Now the direction, that's only the magnitude, right? There's no vector sign there. Yeah.
So, is there ever a situation, is this purely for building the final result that we initially start with saying the integral of B dot dl? Because is there ever going to be a situation where we're not talking about just...
There are lots of situations where it's not that way. We'll get to one real soon. But as the next slide says, we're not going to use this in that situation because it's going to be beyond our mathematical limits usually. Not always, but usually. So this here tells us the magnetic field due to the wire. It's only the magnitude. Why do I say only the magnitude? Because when I started up here, I said that B dot dl is either positive or negative B dl, and I'm just going to do the magnitude. So it's one of two directions, either with my circle or against my circle. And experimentally, it was determined that we can use the right-hand rule to determine the direction. So now, as the last step, if I want the magnetic field vector, then I need to apply the right-hand rule. And at any location, I can determine what the direction of the magnetic field vector is. So that's the classic use of Ampere's law. And we will use it in one more situation, but only one more. Excuse me. So I think it's the next slide that says most situations we don't. It might be the one after this. Nope, it's the one other situation, and then we'll go to, and in all other situations we don't use it. So, a solenoid. This is where I ended class on Monday, with a solenoid. A coil of wires. And if I had gone 5 seconds longer in class, I would have had a clicker question that said, do you see an exploitable symmetry here? Because just like with Gauss's law, with Ampere's law, we need some exploitable symmetry, some symmetry that we can, make one of those three cases. Remember with Gauss's law, we had the three cases. Magnetic field was 0, or magnetic field was constant and parallel. In case of Gauss's, Gauss's law was electric field, wasn't it? For Gauss's law, it was electric field was 0. Electric field was constant and parallel to the direction of my surface, or the electric field was perpendicular. Here, instead of the direction of the surface, the area, we're going to have the direction of the wire, but we still need to find one of those three things. So the question would have been, do you find an exploitable symmetry here? Something where I can make every part of my loop has one of those things applicable. The correct answer is a rectangular loop. Now, did you know that from experience, or were you...
I was just reading it.
Oh, crap. Well, you are right.
That's what I said.
We can make this rectangular loop. I'm going to make it red to make it stand out. So rectangle, like...
I think you should give us tests like that. Just write the answers on it.
Write the answers and say, now can you tell me where the answer is found on this page?
Yeah.
Right here. A. I somehow think that I wouldn't be considered a very good teacher by people who are evaluating teachers, only by students who are evaluating the ease of the class. Okay, so there's my loop. It's not a circular loop. A lot of people say, wait, no, that's still a loop because it closes in on itself. Now, on this loop, how many sides do I have distinct sides. How many distinct sides do I have? 4. So even though we're doing this calculus-based, I'm still going to break it down into 4 pieces. And so I'm going to calculate what happens on each of the sides. So let's start with the easy side. In the center, do I have a magnetic field there? Yes is the right answer. Almost finished saying that. Yes, I have a magnetic field there. If I have a solenoid with current going through the wire, each piece of wire is making a magnetic field. And as we saw in class yesterday, in the center of the solenoid, those magnetic fields are all the same direction, so they're adding up to become a very strong magnetic field. On the outside, it's just the opposite. On the outside, the magnetic fields are working against each other, giving us fairly small magnetic field strengths outside. Another way to answer or to think about that, if that doesn't feel very good for you, is to remember that magnetic field lines always loop back on themselves. So this line that comes out here is going to come out and loop back like this. But there's a lot more volume outside of that solenoid that they're going through, so they're spreading out in that volume, getting much weaker because, just like with electric field lines, if the lines are close together, it's a strong field. If they're farther apart, it's a weaker field.
So is this why we're using a ridiculously long box?
Yes, it is. There, in fact, what you do is you take this and you put little, and we're going out to infinity. It's an infinitely long box. Not just a really long one, infinitely long. Okay, so inside, I'm going to go around this loop. I have to decide what direction to go around the loop. Which direction would you go, clockwise or counterclockwise? You said clockwise. Why? That's what I would choose as well.
Because it's going from north to south. Like,
Because in the center of the solenoid, I'm going the same direction as the magnetic field. That's why I would choose clockwise. And so now I'm going to do my circulation inside. So that's just, okay, I can't do a circle on there because that's only part of it. Part of my circulation is going to be the integral of B.dl inside of my coil. And so this, the part that's the straight line inside is this one here. If I do that, what's happening to the strength of the magnetic field as I move along that little piece of wire?
Along the top.
Yes, along the top. It's staying constant. And how's the direction of the magnetic field compared to the direction that I'm going on my loop? The same. So that means when I do my integral of B.dl, it's just going to be in something I kind of need to define, although it's going to drop out in the end. I'm going to call the length of the loop in that direction A. So it's just going to be that constant magnetic field times the length of that piece. So that's just going to be equal B in the center times A. So that's one of our four sides of the loop. So let's go to the next one going around in clockwise direction. What can you tell me about the magnetic field on this long side here? What can you tell me about the magnetic field as it relates to that side of my loop?
Wait, so A you're saying is the length of the box?
A is the width of the box as you see it there, yes. It's perpendicular. Ann answered that as well in case, just to make sure credit is due. She's like, I don't care. Okay, so if the magnetic field is perpendicular to dl, then what is got to change back to this, integral of B dot dl on the side? It's just 0. And it's going to be on both sides because the magnetic field is perpendicular to my side on both sides. Go ahead.
And maybe this is two questions actually. Why are we doing only in the very, very center on that one coil instead of...
Well, this here is part of the side right here. I'll erase that in a second, but that's part of the side, right?
No, I'm saying like the box. Why is the box so narrow?
It's so narrow because I want to make sure I'm staying near the center of the solenoid. Because what I'm going to find is technically the answer in the center, which would be the answer everywhere, is an infinitely long solenoid. And it's approximately the answer for a finite size solenoid. So it's part of the approximation of doing it at the center. If I did it right at the edge, we would have significant curvature that I'd have to deal with on the sides.
That was my second question. Okay.
Yeah, the actual analysis here, you say, imagine a very long, approaching infinite in length solenoid. In fact, I believe I have those words up here somewhere. Yes. Take advantage of the... it says down here, take advantage of the infinite length to make a rectangular loop. That's taken advantage of if the solenoid was infinitely long. And if I keep my picture in the center, the geometry still works out for the center part. Okay, so the circulation on the side is 0. What about at the end out here?
Assuming we're infinitely far away.
We're
Shouldn't be-
infinitely far away from the solenoid.
So shouldn't be zero.
The magnetic field is 0 if you go infinitely far away. Because the magnetic field is getting weaker and weaker as you go farther away. And as long as you maintain the symmetry that the sides have 0 circulation on them, you can go as far as you want.
How did
Yeah.
it circle back on itself? It actually vanished in the process.
The circling back, remember the spacing between the lines is what tells us the strength of the magnetic fields.
Right.
And the farther away you go, the bigger the spacing between the lines. Until you get infinitely far away where the spacing between the lines is approaching infinity. Hence, 1 over infinity is 0 is the strength of the magnetic field out there.
So I guess my question is, what does the line truly represent then? Because if the strength of
The magnetic field line?
yeah,
The magnetic field line is a line of force. So what it really represents is, now it's different than electric field. If you'd ask an electric field, it's real simple, right? It simply represents the direction the force would be on a charge if it was an electric field. If it's a magnetic field, things are a little more complicated because magnetic fields create torques on other magnetic fields. So if I had another magnetic field here, it's the direction that it would, put a torque for it to line up. But that's what it really represents. And the spacing between them represents the strength with which that torque is going to be applied.
so even though it has no strength, it still technically exists
The
at an infinite.
the strength is not indicated by the line, just the direction. And so if you have, the lines start becoming meaningless when you have, so I have a billion parsecs from one line to the next line, right? They're pretty much meaningless at that point because the strength is pretty much 0. And so it's hard to say there's meaning to it anymore because it's meaningless because the strength is meaningless at that point.
So when we talk about looping back on itself, mostly we're just talking about in the immediate vicinity of the magnet.
For as much as we can measure, they're going to be looping back. It's only when we get below our measurement limits that we say, okay, well, we can't measure it anymore.
Sorry.
But then we're going to, So if I do my circulation, I've now done all 4 sides, because this one here was times 2, right? 2 of the long sides. And so my entire circulation, so now I can go back to showing the circle there, is just equal to the magnetic field in the center times A, the length of my loop. Or the width of the loop, I mean. Well, that seems all good and fine. What was our goal in starting this? What are we trying to find? Yeah, we're trying to find that magnetic field in the center. So this is great because I only have the magnetic field in the center in my answer. We often, I start this and I forget. Yeah, we're trying to find the magnetic field when I do this application. So now that I have that, I have to look to the other side of the equation. The other side of the equation is it's equal to mu 0 multiplied by the current enclosed. Well, how much current is enclosed by my loop? The correct answer is it depends, but it depends on what?
A.
The number of loops that go through, which depends on A. So what we do is we define a new variable. Lowercase n is the number of loops per unit length in my solenoid. So lowercase n might be 1,000 per centimeter. That means I have 1,000 loops per 1 centimeter of length in my solenoid. And then the number of loops enclosed is equal to the number of loops per unit length multiplied by the length of my box, the width of my box. Right, capital N over capital L is just telling me the space in between them, And now if I know how big a section I have, I can tell you, okay, you included this many loops. That means the current enclosed is equal to the current in the wires times the number of loops enclosed, which would be I times NA. So now I can put it all together to get my final result, B center times A is equal to mu net I N A. Now, I made up this variable A because I said, well, I have to have it because we have to have some length. But I also specified at that point, it doesn't really matter because what's going to happen to it? It's going to divide out. If it didn't divide out, I would have a flawed derivation. Because what it'd say is, well, you choose a different size box and you get a different magnetic field in the center. So the magnetic field in the center is completely dependent on what you chose. Right? That shouldn't be it. It should be based on physical, what's the current, what's the radius, and so on. So what we end up with is the magnetic field in the center is equal to mu naught times current times the number of loops per unit length. That is our second and final application of Ampere's law. Yeah. Now, we might have homework problems that ask you to find like B dot dl for a stretch of wire that's at an angle or something. But in general, this is what we do with it. Other things just become overly complex. And I will grant the Biot-Savart law is not simple. But it at least is, in many cases, going to be simpler than using Ampere's law. So any question about this derivation here? We're going to see an abbreviated form in class tomorrow. You have a question? Look, he's got water. It's actually empty, but it's a principle. I mean, after all, the only reason I'm enforcing this is principle, right? All right. Things to keep in mind here. What difference does it make to the strength of the magnetic field in the center? I'm going to just come up here and rewrite the equation. What difference does it make to the strength of the magnetic field in the center of that coil if I have bigger radius loops? None. Makes no difference. It will make a difference to our original assumption of has to be a solenoid that's long compared to its radius. I didn't say compared to its radius, but that's how you actually determine if it's long. If it's long compared to its radius, then it's a long solenoid, and this derivation is accurate. So if its length is like 100 times the radius, this is going to give you the right answer for everywhere except for the very edges. So radius doesn't matter as long as it's much longer than its radius. Okay, a second question. What difference does it make if I have my loops wrapped closer together? It's going to increase the magnetic field. The closer I can put those loops, the stronger the magnetic field. What about uniformity inside of there? I drew my box to the center. But would it have made a difference if I had drawn my box so it just was barely inside?
Yes.
Okay. As long as we have a long enough solenoid compared to the radius so that we don't have any curvature, it's still going to be zero flux in that portion that I just marred and will erase in a second. Or not zero flux, but zero circulation for that portion because the magnetic field is perpendicular to the length. So it actually didn't matter if I was at the center or near the edge of those loops. So everywhere across, everywhere inside the solenoid should have the same magnetic field. Once again, provided that we're not at the edge and that it's reasonably long. So it's a very uniform magnetic field in there. Now, I'll talk one final thing that's just hand-waving. You'll see a picture of it for class tomorrow. It was actually on the last slide I showed in class yesterday. there is a certain coil that's called a Helmholtz coil. And a Helmholtz coil is created by making one loop here and one loop here. And I believe it's the separation is equal to the radius. I didn't look it up, so I could be wrong on that. It might be the separation is equal to the diameter. But it's a specified relationship between the radius and the separation of the two coils. Actually, we have a Helmholtz coil. I'm thinking about its dimensions, and yeah, it's got to be the radius like I drew. The reason that we have that special Helmholtz coil is because that provides a very uniform magnetic field in this region between them, while giving you an opening that you can put things in and take them out of. And so it's a more convenient way of getting that uniform magnetic field. What you're taking is, this here would naturally come up like this, and this here would naturally go like this, and when you add them together, they add to give you what the same behaviors if you had a long solenoid. Yes, it's smart.
And this would be used to magnetize something?
For anything where you need a strong magnetic field. So let us suppose, I actually watched a how it's done thing on how they make MRIs. And it's really, really interesting to watch how they make the actual MRI, because they're making a coil. Now, it's not a Helmholtz coil for the MRI. It's more of a solenoid. But this coil is going to have extremely high currents, and it has to be very precise, and so they're all handmade. It's not machine wrapped. Adds to the expense. I mean, their machines do part, but then you have to make all of your adjustments to get that uniform magnetic field in there. Because if the magnetic field is non-uniform inside your MRI, then you're going to have some variation in the results, and it's hard to deal with that. Okay, so we only used Ampere's law where it was convenient. Where it's not, then we go to the Biot-Savart law. And now is where Toussaint can correct me. Much like the name Toussaint, Savart has two consonants at the end, and it slays me. If they just put it like, I don't know how you draw that. If they just spelled it like that, I'd be totally fine with Savart. But no. It's a dude's name, and it's Biot-Savart. Right, Toussaint?
You pronounce the R.
No. I have looked it up. You don't. At least, I mean, that's, you listen to the pronunciation. Savart. You go down at the end instead of up, like I think people say Savart, but
R is
yeah. But let's just say I don't have an ear for the language and go on. Okay, so what does the Biot-Savart law do? It relates the magnetic field to the current, once again, but now instead of a dot product, what do we have? A cross product. Huzzah! Now we can do an integral with a cross product. I'm not sure we've done that in the past. So we're going to do this. Now I have two different forms written here. ds means a little infinitesimal piece going along the length of the wire. So this is for calculating the magnetic field created by a single wire. Now if I have multiple wires, I just have to go through all of the wires. ds is a piece of length of the wire. I is the current through the wire. And then we have r hat, which is the direction going from that piece of wire to where I'm finding the magnetic field.
So are we saying ds is the same as dl then?
Yes, in the picture, it uses D capital L. In one of the pictures on the coming pages, they use a D lowercase l. I think it's on the next page. And you will see why that's a really poor idea. They have I for current and lowercase l for length. You're like, seriously? But then uppercase L is bad because uppercase L stands for inductance. And yeah, things get really confusing. So Your variable choice, you'll see lots of people making different choices for the names of the variables simply because it starts to get confusing keeping the variable names straight.
You should just start drawing pictures at this point.
Do what?
A loopy lowercase.
Yeah, loopy lowercase l is what, people who use L try to, but as you'll see on the next one, their lowercase l is vertical. That's how they indicate that it's not current. The current is italicized and the lowercase l is not. You have your method that through some divination you can determine. Okay, notice I have this written two ways, one with the r hat, one with the r vector. Obviously, since r vector is equal to r magnitude times r hat, this one here has r cubed on the bottom. This one here only has r squared on the bottom. It's important that I point these out so you don't think that there are some, they're two different equations. It's just two different forms that mean exactly the same thing. I write the two different forms because depending on your situation, you might prefer one compared to the other. So let's go forward and look at a problem. Somebody asked me at the end of last class period about the magnetic field due to a circle. It's actually the one after this. So I'm going to go to it just so you can see the picture. You see, this is the picture where that is an L, dl, and that is an I, and, okay, you can't see what I was pointing to. There's dl, there's I, and you really have to be paying attention to keep those two separate. This is the way, using the Biot-Savart law, that you can calculate the magnetic field at the center of a single loop. Right? We did a solenoid. The solenoid was making the approximation that it's long compared to its radius. Well, a single loop, that certainly is untrue. So we cannot take our solenoid result and try to apply it to a single loop. It simply can't be correct. So let's do at least one of these two problems. Hopefully we'll do both. So the first one, let's find the magnetic field due to a single wire with current I going through it. Does this sound familiar? How many people remember when class started?
Today?
Yeah, today.
Nope.
This is what we did to start class. So it should be familiar. But when we started class, we used Ampères law to find the magnetic field due to a single wire. And we invoked some symmetry rules and things like that. Now we're going to look at the same problem, but do it using the Biot-Savart law. So in Ampères law, what were we integrating over? Which was?
Length of the wire or solenoid thing.
It was the length of our imaginary loop. An imaginary loop that didn't even exist. When we're using the Biot-Savart law, what are we integrating over? The length of the actual wire. We're integrating over something that actually exists. So the path is chosen for us. We don't have to try to find a tricky path. The path is set for us. And then we just have to do the work. Now the first thing to do is to identify your directions. So I have ds cross r hat. How do I find the direction for ds cross r hat? Looking at my picture, what direction is ds? Up, right? It's got that little blue arrow. S is the length of our wire, and ds is going up. So ds is pointing up. What direction is r hat in the picture? Okay. Going to, let's just say rightish, okay? It's going rightish. It's going right and down now, but if I was looking at a piece down here, it would have been right and up. So it depends on what piece I'm looking at, but it's always going to be right of the wire. So now, how do I find the direction of that cross product? And that's right. Right-hand rule. So right-hand rule, always the same thing. How do you apply the right-hand rule? What's the first thing you use when you're applying? I want somebody to lead through the thought process of applying the right-hand rule. Not your thumb. Index finger. And what direction should the index finger point?
Same direction as ds.
The same direction as the first element in the cross product. So in this cross product, it's ds cross r hat, so my index finger is going to be parallel to ds. So now I have to have my hand, so my index finger's pointing up, and it's going to have to stay up, much like the song. This is the light of mine, I'm going to let it shine, right? Stays up for this problem. Then I need to orient my hand so my middle finger can point the direction of what?
The right. R.
R. The second element that is in my cross product, which in this case is r hat. So my index finger is staying up, my middle finger is pointing in the direction of r hat, and then my thumb tells me that's the direction for the cross product. So my cross product is into the screen. If I'd done it down here, it still would have been into the screen. So for every piece of my wire, it's into the screen. Hooray! That makes my problem easier. Not all problems are going to have the direction is the same. So I can take this, and that's the first thing I evaluate. Whoops. I determine that ds cross r hat is into the page. Now, of course, if you go around the wire into the page, is changing directions, but we can deal with that at a later date. So in our picture, ds cross r hat is into the page. What would the value, the magnitude of ds cross r hat be? By definition, magnitude of r hat, which is clearly 1. And then, go ahead, you said? Sine of theta. So since magnitude of r hat is stupid to write magnitude of r hat because the hat means it's 1. So that means that this ds cross r hat, I can just put in my equation as ds sine theta for its magnitude. The direction is into the page. So I'm going to do a scalar calculation now with my direction into the page and my magnitude for that cross product being ds sine theta.
Question.
Go ahead.
Is the theta that's in the picture the appropriate theta?
Yes, it is, because theta is the angle between the two things in the cross product. That is an important question to ask. Because, I could define like this angle here. That's a different thing, right? So that's an important question to ask. So now I can put dB vector is equal to mu naught over 4 pi I over r squared ds sine theta into page. Right, the into page is my direction. I'll put a hat over it. It's a unit vector. Into the page. Now, I'm going to quickly just say dB magnitude is equal to mu naught over 4 pi I over r squared ds sine theta. What do I do with an equation like this? You made me laugh and spit. What do I do with an equation like this? How could this possibly help me in any fashion? I don't know is at least an honest answer.
I don't understand.
What we're trying to do?
Oh, now I understand. No, I don't.
We're trying to find the magnetic field.
I assume
That's what we're trying to do.
Right, but why are if we're looking
You're
for the,
right.
Sorry, you were going to say something.
Well, no, I want to hear Chad's questions because I want to make sure we clear up questions and not say, let's push the questions to the end and maybe we'll forget about them. It's not the way to teach.
This last doesn't work. So, why are we not using the bottom equation? Just
In this case, it's mostly personal preference. I would have had an r on top if I'd used the bottom equation, and then I would have had an r divided by r cubed, which is 1 over r squared, and I would have had the same answer.
oh, okay. I gotcha.
Okay, we're trying to find b, and if I have db, how do I go from db to b? We integrate, right? There may have been one of your homework problems that didn't have integration, but this one has integration. So we integrate this side and we integrate this side. Well, the left side, what am I going to get when I integrate dB? Hey, very good. B. On the other side, what's my variable of integration?
Yes.
ds. R is also a variable. So I have two variables on the right-hand side. So what do I need to do? Actually, I have three variables. R is a variable, theta is a variable, and S is a variable. S is telling me my vertical position. Theta is related to the vertical position, but that's the angle between ds and r hat. And of course, r is the distance from ds to p. So what must I do? Okay, I was closest to him. So what did you say?
Put it all in terms of S.
Put it all in terms of S. What did you say?
I just said relate them to each other.
Relate them to each other. Now, you can put them all in terms of S, but it turns out the calculus is much easier if we put them all in terms of the angle. So I'm going to do just like you did on problem 1, part B, putting them all in terms of the angle. So I start and I say, I have a constant of capital R, the distance to the wire. And so R squared is equal to, in relation to R and theta, well, let's do R instead of R squared. In relation to R and theta, R, capital R, well, I'll write it this way. Now I have something that is an interesting thing. If I take this angle that's bigger than 90 degrees, I take the sine of that, I get a value that's finite between 0 and 1, right? Is that the same as if I took this angle?
No. Yes.
Yes, it is. So I can still say sine theta is equal to R over R, opposite over hypotenuse. That's kind of an important thing to realize, that even though it's an angle bigger than 90 degrees, it's still going to give me that same relationship. Because we always, these definitions of opposite over hypotenuse, that only applies for angles between 0 and 90 degrees. But we have, when we look at this, the supplement, the sine of the supplement is equal to the sine of the original angle. So sine theta is R over R, which means that lowercase r can be replaced with capital R over sine theta. Right? So now I am able to eliminate one of my variables, the R variable, and replace it with theta, but I still have to work with the ds. The ds is the part that was more complicated from your work in the homework. Remember, we had tangent of theta was equal to capital R over S. And in this case, we actually have a sign variation. Take the derivative of both sides of that, and you had d theta over cosine squared theta was equal to, I should just use a different angle. I need S on the opposite side for that to work out for me nicely. So, okay, I'm going to change from theta to this angle here that I'll call phi. I'm going to change that for the simple reason that my derivation there, I have to go to something different. If I use that angle phi, then of course sine of theta is equal to cosine of phi. So that's just a straight shift from one angle to another angle. Because theta and phi are themselves, well, this theta is supplementary to that, and then that's complementary to that. What was that?
Could you just use cosine theta?
Well, theta is this angle, and I'm changing to that angle. So that's the first shift, just to get into phi. Then the second shift, using phi, I would have cosine of phi is equal to capital R over R. So lowercase r is equal to capital R over cosine of phi. And then I have the final one, tangent phi is equal to S over R. Derivative of tangent phi is d phi over cosine squared of phi is equal to ds over r. So here is how to get the ds converted into a d phi, and here is how to deal with the r. And so if I substitute those in, so there I substituted for the 1 over r squared, and then for ds, I have that, and then for sine theta, I have cosine phi. So now I've made all my substitutions, and let's see what we can cancel. I can cancel cosine squared, 1 over cosine squared phi with cosine squared phi. Those cancel out, which is really nice. And then this is an r over an r squared. So I'm going to be left with 1 r on bottom. And that integral. And then I look at my limits. If I'm going an infinitely long wire, because that's what we did for class, beginning of class, then I'm going to be going from minus pi over 2 to pi over 2. What's the derivative of cosine of phi? Or, I meant to say integral, but yeah, you said it right. No, it's just sine. Yeah, I said it wrong, but yeah, you answered my question right. I said it wrong. So I have minus sine of phi from my yeah. It makes a difference. It makes a big difference. It makes a difference of right versus wrong. Okay, so when I put in those limits, what's sine pi over 2? One. And sine of minus pi over 2? Negative 1. So this entire thing here is 2. So I have mu naught I over 2 pi r. And now we can breathe a sigh of relief because we found the same thing that we found with Ampere's law. Next class period, I'll do the BiotSavart Law on one more thing. Okay, we're at time. Sorry, I went a little bit late.